Welcome everyone. Thank you all for being here. Today we are joined by theoretical astrophysicist, researcher, and one of the most popular scientists on Twitter, Katie Mack. Katie is the author of The End of Everything, Astrophysically Speaking, and is a science writer for Slate, Time, and Scientific American. In this live stream, Katie will take you on a trip to the end of the cosmos, exploring the possible big finales anticipated by science. It is my pleasure to welcome Katie Mack.
Hello. Thanks so much for having me, and thanks to everybody who is here to listen to me talk about ultimate destruction. So I'm just gonna share my screen and start the slideshow. Just a moment. Hold on a sec. Wait, hold on. Sorry. Okay. There, that should work. Apologies for the momentary technical blip there. All right, so I will be talking about how the universe might end, and I'll talk about a few different possibilities for that and what we are learning about the end of the universe and how we're figuring it out. When I give this talk, I sometimes like to start with a little poetry. Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. That's the famous poem by Robert Frost from 1920. Of course, now we know the answer, it's fire. It's definitely fire. In around 1 billion years, the sun will become so bright that it will boil off the oceans of the Earth. A few billion years after that, the sun will engulf the orbits of Mercury and Venus and leave the Earth a charred, lifeless, magma-covered lump of charcoal, at which point, as the sun sloughs off its outer layers, the Earth will very likely then spiral into the sun and be completely destroyed in the stellar plasma. So that's it for the Earth. We know the answer to that one. But as a cosmologist, I'm interested in a bigger question. I'm interested in the universe and how the universe itself might come to an end. So in the book that I've just written, The End of Everything, I talk about 5 different possibilities, and I'm going to sort of quickly breeze through those here. If you have questions about them, I'll try and answer some at the end, but also there's much more detail about all of this in the book, as you might imagine. So I'll talk about the Big Crunch, the heat death, the Big Rip, vacuum decay, and bouncing cosmologies. But just to orient everybody, I'll start here. So we are in a galaxy. Depending on where you are, you may or may not be able to see that we are in a galaxy, but if you are in a dark sky location, you might see something like this, a stripe of stars stretched across the sky with dust and gas in between, and sort of bright bulge in the center, depending on where you are looking at it from. If we were able to step outside of our galaxy, it would look kind of something like this. This is actually our nearest large galaxy neighbor, the Andromeda Galaxy, but we have similar properties. The Milky Way galaxy looks a lot like the Andromeda Galaxy. Billions of stars, a collection of stars at the center, gas and dust, and various things sort of orbiting around. And when we look out into the cosmos, we see billions or possibly even trillions of other galaxies in our observable universe. This is the Hubble Ultra Deep Field image, and this image contains in it something like 10,000 galaxies. Each of these little bright, colorful smudges in this image is a galaxy with its own set of millions or billions of stars. And everywhere we look, we see we see galaxies, no matter how dark a portion of the sky we look at. If we look deep enough, we see galaxies as far as our telescopes can see. And sometimes they just look like these little bright smudges. But one of the things that we notice about these galaxies when we look out into the cosmos is that in general, galaxies are moving away from each other. The universe is expanding, so the distances between galaxies is getting larger. And so when we look out into the cosmos, we see that on average, everything is getting farther apart, the universe is getting bigger, which suggests that there was a time when the universe was smaller and more compact, and in fact suggests a time that the universe was so small and so compact that instead of being sort of dark and cold and empty, space was hot and filled with plasma, filled with the sort of fires of creation. We can dial that expansion back and see that implies that the universe was born hot, that there was this what we call the hot Big Bang, or the Big Bang theory is really the idea that the universe was at its earliest times hot and dense and filled with this sort of glowing plasma. And this isn't just a hypothetical. We see very solid evidence for the universe being hot and dense in its early phases. And when I say we see very solid evidence, I actually mean we see that. We see the universe being hot and dense in its early times because we can see the universe in its early times. We can see the early past, the early history, the beginning of the cosmos. We can see the end stages of the Big Bang itself. The reason for that is that when we look out into the cosmos, the farther away we look, the farther back in time we're looking. So if we were looking at, the sun, we'd be looking at about eight and a half minutes ago. If we were looking at another star, we might be looking at many years ago. And if we look at another galaxy, we might be looking at billions of years ago. And so it stands to reason that the farther you look, the farther back in time you see. So here's a diagram of that where, in this diagram, we have the Hubble Space Telescope looking out into the distance, and this purple band is the Hubble Ultra Deep Field, that image I showed you with all those tens of thousands of galaxies in it. And when we look at those galaxies in the Hubble Ultra Deep Field, we're looking at galaxies that existed when the universe was only about 500 million years old. It's currently about 13.8 billion years old. So we're looking at some of the earliest galaxies in the universe. But what happens if we look past those earliest galaxies? What happens if we look at a time before galaxies existed, before stars existed? We can look back so far, we can look so far away that we're looking at a time when the universe was still on fire. We can look directly at that early hot phase of the Big Bang, because the Big Bang didn't happen at one spot. It happened everywhere. The whole universe was hot and dense at its early stages, which means that if we look far enough away, we're looking at a part of the universe that's so far away that light took 13.8 billion years to get to us. And the light that gets to us is the light from that early glow, from those first moments when the universe was hot and filled with plasma. We can actually map that out. So if we look out at the universe in visible light, we see something like this. So this is a map of the whole sky in visible light with the globe of the sky around us transformed into projected onto an oval map. And this is what the sky looks like with visible light. If we look at the sky with microwave light, we see that afterglow of the Big Bang in every direction. And we see it in every direction because every direction we look in, we can look far enough away that we're seeing that first light. And it's remarkably uniform. It looks kind of like this. If you were to take that microwave light and transform, assign microwaves a color, it would look like this. It's very, very uniform, but we can crank up the contrast on that image, and then we get something that looks more like this. So this is an image of the cosmic microwave background, this background light from all around us. So one of the first images that showed that there was some variation in that cosmic microwave background light. Now these variations that you see in this image are differences in temperature or color of the microwave light of about 1 part in 100,000. So they're very small variations, but we can see that there's a little bit of variation across the sky in that afterglow of the Big Bang. And we can also analyze the spectrum of that light, which means that we can take that light and sort of separate it out like in a prism where we sort of separate out the colors. But in this case, we're talking about microwave colors. So, sort of frequencies or wavelengths of microwaves. And we can see how bright it is at each of these colors. And we get a very characteristic curve, a very characteristic distribution of light at different colors of microwave radiation or different frequencies of microwave radiation. And this is called a blackbody curve. And the reason that this is important, this distribution of colors of that light, is because that's the same kind of spectrum, the same kind of distribution of colors that you get with anything that's glowing because it's hot. So this image here is of a poker that you've stuck in the fire, and it's gotten red hot from being heated up, and that glow, that red hot glow, if you were to decompose that light, chart out how much of that light is in the red and the yellow, and figure out the distribution of that light and intensity at different wavelengths or different colors, it would be exactly the same kind of shape as the light we get from the cosmic microwave background. This characteristic shape occurs for anything that's glowing because it's hot. And that's what we see in the universe. We see that the farthest away we look, the universe itself is glowing because it's hot. That's what we can see when we look out into the farthest reaches of the cosmos. And this is a very, very perfect, it's called a blackbody curve, which is this spectral shape. It's a very perfect curve. These little boxes on the curve, those are the error bars, the uncertainty in the measurement. And those are magnified 400 times, because if we actually showed the uncertainty in the measurement, you wouldn't be able to see it behind the little line of the idealized blackbody curve. So it's the early universe really was just glowing because it was hot. So we can take that light, and we can get even better precision on that map. And in recent years, we've gotten a really beautifully detailed map of that background light, where, again, this is just tiny contrasts in the color or temperature of that early glow. And we can see that there are parts of the universe where it was a little bit hotter, parts where it was a little bit cooler during those first that first time when the universe was still hot and dense. It was technically about 380,000 years after whatever the first moment was. That's how long it took this sort of primordial fire to start to cool. And so we can see that there are places where the universe was a little bit more dense, a little bit less dense, this sort of cosmic plasma. And we can use our calculations to see how those little places where there's a little more density, those are the places where we got galaxies and clusters of galaxies forming out of that initial fire. And then the places where there's a little less density, so you get giant voids in the universe and so on. So we have this beautiful picture of the very, very beginning. And perhaps surprisingly, looking at the very, very beginning, looking at this earliest phase of the cosmos, we can learn a lot about the end, because we can use these images to study the early conditions for the universe, but also what's in the universe, what's in the universe between here and there, where there is the farthest we can possibly see. And these images can tell us something about the behavior of the very early universe and what it was made of at that time. And then we can use extrapolations, and we can use that to learn something about how the universe will evolve in the future, and how the universe might end. And so this is one of the best tools we have for studying the future of the universe, even though what we're really looking at is the past. So now I'll go through a few of these possible futures of the cosmos. I'll start with the Big Crunch. So this is a fairly simple idea that's been around for quite a while. I mentioned the universe is expanding, and so there's been a question for a long time: will the universe continue to expand forever, or will it at some point stop the expansion and recollapse? So, will we get to a point where the universe is sort of maximally large, but then all the gravity of all the stuff in the universe starts to reverse that expansion and bring everything back together again? And what would happen if we did that? Well, the first thing that you would notice if the universe really were recollapsing is you would notice that galaxies would start to interact with each other. They would start to collide. So this is an image of two galaxies that are currently interacting with each other, where you can see that these galaxies are coming together. They're flinging stars off in these long tails. And we see this all over the cosmos. We see places where galaxies are colliding with each other. and creating these beautiful tendrils of stars that are being sort of flung around as these interactions occur. And the other thing that happens when galaxies are colliding like that is you get these big bursts of star formation, because you're bringing all the gas from these two galaxies and smashing it together. And that's one of the ways to sort of spark the formation of new stars. And so that's one of the first things that you would notice if the universe were starting to collapse, is you'd have more of these galaxy collisions. And you would have you would see many more galaxies in the sky. But the collisions between galaxies are not really the catastrophic part of the Big Crunch, if the Big Crunch is happening. It's not what kills the stars, because even when galaxies are colliding with each other, within galaxies, stars are really very far apart. There's a lot of empty space in galaxies. And so the stars are much more likely to miss each other, even in those big galaxy collisions, than they are to actually smash into each other and collide and be damaged. So if anything were left of our solar system when a galaxy collided with it, and there is one coming for us, I should mention, the Andromeda galaxy is heading for us right now and will hit us in about 4 billion years. Not a sign of the Big Crunch coming. It's just because our galaxy and the Andromeda are already pretty close together, and they're already on their way to collision, whether or not the rest of the universe does anything particularly exciting. So even when that happens, like, the solar system probably won't be terribly disturbed by this, but if the Big Crunch were coming, if it weren't just a collision of galaxies, but actually the whole universe compressing, then you would see something much more dramatic, which is that, there's all this background light that's already in the universe because it's leftover light from the Big Bang, the cosmic microwave background. That's been dispersing through the cosmos and cooling for all these billions of years. If the universe were compressing, that light would be compressed and get hotter and get more intense. So the background light would start to heat up as we get closer to re-entering that sort of cosmic plasma phase. So you would notice that the background light got brighter, but it would be worse than that, because in the history of the universe, it's not just this background light that's out there. There's also all the starlight from all the stars that have been shining in the billions of years that the universe has had stars. And so that starlight right now is just dispersing through the universe and getting more diffuse and just sort of spreading out. But if the universe were compressing, then all that starlight would be compressed. All of the X-ray and gamma radiation that's been produced by high energy processes in astrophysics, all of that would be compressed. And that's what kills the stars, because at some point you get so much intensity of radiation just out there in empty space that it starts to actually ignite the surfaces of stars. And you would get these thermonuclear explosions across the surfaces of all the stars. And that would be truly unsurvivable. So if the Big Crunch were coming, that's how it would go. But we think probably the Big Crunch is not coming, because based on our current observations, it really looks like the expansion of the universe is not going to stop and turn around. It looks like we're going to head to a different kind of future, which is called a heat death. So the heat death is where the expansion of the universe continues and continues and continues, and actually starts to speed up, or has started to speed up. So in the 1990s, it was discovered that not only is the universe's expansion not slowing down from all the gravity of all the stuff in the universe, it's actually getting faster. And this is a very strange result, because it was thought before that there are only really two possibilities. Either the universe is slowing down in its expansion and will at some point recollapse, or it's slowing down in its expansion, but the expansion will still win. It's just it'll always be kind of slowing down and getting bigger in a sort of slower, gentler way. And as it happens, when that was really measured, the universe is not slowing down at all. The gravity of all the stuff in the universe is not slowing the universe down. It's the universe is actually speeding up in its expansion. It used to be slowing down, and then about 5 billion years ago, it began to speed up. And we don't know why that is. Whatever's causing that expansion to happen, to speed up, we call it dark energy. And I'll talk in a minute about what that might be. But whatever it is, it means that galaxies are getting farther and farther and farther apart from each other, faster and faster all the time. And what that means for us is that in the distant future, other galaxies, distant galaxies, will become invisible to us. They'll be carried away so quickly that their light will not be able to reach us. And so over time, we will be increasingly alone in the cosmos. In about 100 billion years, it will be impossible to see galaxies beyond our little local group of galaxies, Andromeda and the Triangular Galaxy and Triangulum Galaxy, and this little group of galaxies around us, which we will have merged with by then. But external galaxies, all those beautiful galaxies we saw in that image of the Hubble Ultra Deep Field, none of that will be visible. We won't even be able to see the cosmic microwave background light. The universe will appear dark outside of our little pool of light of our own little sort of super galaxy that will be the result of these local collisions. And so once that happens, there won't be any more collisions of galaxies to form new stars. We will have used up all of the gas in our own galaxy that stars are made of. And so our galaxy will be left with just a whole lot of dying stars, sort of fading away. And these stars will fade away. The black holes in the galaxy will start to evaporate away. Matter will decay, and eventually everything will kind of just fade out. There will be no structure left in the cosmos, and that's called the heat death.